Hello everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland joining PhD program. I am the TA for this course, Applied Optics. So let's start the discussion for today. Today we'll discuss. Today we'll discuss interference by division of amplitude mainly. Last day, we discussed the interference by division of wavefront. So we'll see what are the difference between these two and how we will use this the knowledge for the interference from division of amplitude. So uh, a quick recap of all the classes, a very quick recap. So that if a plane wave falls on a surface, some part of the wave is transmitted and some got reflected. That amplitude of the incident wave then divided into transmitted wave and reflected wave. This how we get the division of amplitude. And in some experiment, you will see that the wave when falls on a thin film, the wave reflected from the upper surface and the lower surface. So basically the thin films are like this. So this is the wave and it get reflected also. And then reflected one refraction, then a reflection here, then another refraction. And so on and so forth. These wavefronts can get fall superimposed with each other and give you a interference variance. Similarly, at this point, not all the waves got reflected. Some of them reflected also. This set of beam can also give you an interference pattern. Both set of beam will give you an interference pattern. Always remember that. So, predominantly, we will interference pattern fringe also due to this beam of this set of beams, but we get both of them. So in the class, we have this set of beams. So first, we first start with thin film double beam interference. So, thin film. So always remember what is called thin film. Thin film when the thickness of the film is of the order of the wavelength of the light. So the film thickness is not a fixed like dimension for all the wavelengths. It depends on the wavelength, whether it is called thin film or thick film. So our discussion for interference solely focused on thin film, and the film will be called thin when the thickness of that film is order of the lambda of the light we are talking about. So we have seen that the optical path difference between uh, two beam, this beam and this beam, where this is the theta t, optical path difference is 2nf. This is n1, this is n1, this is n2. 2nf, this thickness is d cos theta t, and this angle is theta t cos theta t. And this is the optical path difference. The phase difference is basically k naught into lambda. So basically k naught plus or minus pi. So here due to reflection, there is a phase shift. So we take minus sign basically for the simplicity of the equation. So we take minus sign here, and we know if n this is equal to 2n pi, we'll get bright fringes or constructive interference. So this give you the formula d cos theta t is equal to 2n plus 1 lambda f by 4. Lambda f is equal to lambda naught by nf basically. And when delta is equal to 2n plus minus 1 pi, we will get dark fringes or destructive interference. So that gives us 2 cos theta t is equal to 2n lambda f by 4. So here we need to remember one thing, that if, let me write in, if n1 is greater than nf or greater than n2, or n2 greater than nf, and nf is greater than n1, pi phase shift will not be there, and the equations will change that way. So till now we are like here in the equation you can see the thickness is the same. Thickness is same. Angle is varying. basically. This kind of fringes are called fringes of equal inclination. But when the thin film is made by this wedge kind of surface, here you can see the thickness is changing and inclination was the same, almost same. Those fringes are called fringes of equal thickness. So in fringes of equal inclination, thickness is constant. In fringes of equal thickness, the angle is constant, almost, or small. Okay, for wedge-shaped films, if this apex is alpha and at position xm we want to see the fringes, so condition for maxima is m plus half of lambda 0 nf dn. So d is the basically thickness edge for mth fringe. So, and also we can write d as alpha into x m. So dm will be alpha is equal to xm. So that equation becomes m plus half of lambda naught is equal to 2 alpha xm nf. So from that we get that xm is equal to m plus half of 2 alpha lambda f. So when we put m is equal to 0, 1, 2, and 3 successively, we see that maxima occurs at distance from apex. So this point is called apex basically. Apex given by lambda f 4 alpha, lambda f 3 lambda f 4 alpha, and so forth. So delta x basically lambda f by 2 alpha. When lambda f is 0, we see that beam reflected from the lower surface traverses the film twice. So the maximum differ in optical path length by lambda f by 2. Not 0, lambda is equal to 1 basically. Now we firstly we can discuss what is the difference between fringes of equal thickness and fringes of equal inclination. So first, fringes of equal inclination. This is also called Fizeau fringes. So it happens when light reflects from thin film varying thickness. But constant angle of incidence. So here, when we were discussing this wedge kind of thin film, we assume that cos theta is all equal to 1 because theta is very small. So that's as constant. Okay. So the fringe pattern for this kind of fringes is straight, parallel, and perpendicular to the direction of thickness variation. And where they occur? So in air wedge or thin Michelson interferometer. Not all Michelson interferometer fringes are fringes of equal thickness. It happens when the mirrors are inclined at a small angle. And by these fringes, we can test the thickness of air films. And each fringe here represent the points are having same thickness. Now, fringes of equal inclination. So it occurs from an extended source illuminates a film of uniform thickness. Is of uniform thickness. That source illuminates the film with interference resulting from rays at different angle of incidence. So this is the reason of fringes of equal inclination, and these fringes is also called high danger fringes. So fringes of equal inclination means in each black fringe or bright fringe represent where the inclination is same, but consecutive dark or black fringes doesn't have the same inclination. All over the layer of a thin film is uniform. But for fringes of equal thickness, the inclination is almost same, or angle is so small that cos theta term got 1 is equal to 1. So then we get fringes of equal thickness. There the inclination is same. Each fringe corresponds to the point where the thickness is the same, but two consecutive dark or bright fringes occur due to the different thickness. So this fringe pattern is circular generally. Centric rings centered on the optical axis. And the fringes are localized at infinity. That means to see the fringes, we need converging lens or telescope. But here, to see these fringes, they are localized within the film and can observe directly. when does this fringes of equal inclination happens? So it happens in corner. So they basically occur in February interferometrage. Parallel films. Michelson interferometer, but when the mirrors are exactly perpendicular. So the practical application for these fringes of equal thickness and fringes of equal inclination are as follows. Precision measurement. So surface testing, or we can say flatness testing, coating analysis, and we can measure the thing and measure properties. And for the equal inclination application are used in spectroscopy, laser cavity design, interference filter, so on. Sorry, that's equal inclination. Issues. So now we can go back to, so these are the basically the properties of equal of fringes of equal thickness and fringes of equal uh, for fringes of equal thickness. The inclination angle for the thin film or the wedge is like same for each ray, but the thickness they are going through is different. And for one fringe, like at the mth fringe or m plus 1th fringe, for the points in the same fringes, they represent same thickness, but the points, 1 point from mth fringe and the 1 point from m plus 1th fringe, they represent different thickness. And basically, for fringes of equal thickness, they are straight, parallel, and they are localized in the film. But for fringes of equal inclination, the thickness is uniform, but the different point from different fringes, they represent different inclination. All the points from the same fringes correspond to same inclination. But to observe this kind of fringes, they are basically circular fringes, and you need a converging device. So from Michelson interferometer, you get both kind of fringes, but you need to know when you get what. So now we go to the Newton's ring. So like if lenses like this is on top of. So basically, experience and kept on top of an optical flat glass where there is air film between this optical flat glass and the lens. So this is one is plano-convex lens. So I am talking about this portion. This is air and it's the air thin film. So this will, so if a light comes here and it passes through like this, and this gives another light beam, so on. They are the like this. So the light falls in this. It go reflect. So we are considering this film. So light directly goes here. Then one part got reflected, one got refracted. That also got some part refracted and reflected, and that's how you get reflected light and refracted light both. So this is R1, this is R2, this is T1, that's transmitted, and then T. They both Rn and R2 can generate interference fringes, and T1 and T2 also generate interference fringes. So, the thing I wanted to show you. So, R1 and R2 of interference fringes Rn and R2 generate. This is by Rn and R2. This is by T1 and T2. Okay. So, for interference fringes from the reflected light, the center is dark or destructive interference. But for in Newton rings in transmitted light, the center is bright. So no, that the radius of any fringe xn of the radius of the nth fringes is given by 2RD. So this is D. And from the I, if we have an I here, this is R basically, and this is xn. So xn square is equal to 2RD. So the nth order interference maximum will occur in the thin film when its thickness is in according with the relationship. The relationship is 2mf Tm. Tm is the diameter of the emit wide ring, which is equal to m plus half of lambda. Will happen when this for 60 back. So this is constructive interference. So for right rings, it's basically n plus half of lambda f r. M starts from 0, 1, 2, and so on. For dark rings, xn is basically root over n lambda f r. So when the mxn gets larger means the fringes, the outer fringes, here you can see they got thinner and also narrower. So then there is Michelson interferometer, and how the Michelson interferometer. So basically there is a source, there is a beam splitter, one beam goes this way and that beam goes, and one beam goes that way, and these also combines, both of them go together, and here they here. Sorry, my picture here is animal, and where is human seeing the. So this will basically happen 70 kilometer. We get both fringes of equal thickness. Means and fringes of equal inclination depending on setup. As mentioned, that when happens in interferometer, the mirrors are exactly perpendicular, we get fringes of equal inclination because the thickness is same. But when they are at an angle, we get fringes of equal thickness. When fringes are at like the N1 and N2 are at a which we get equal thickness and for equal inclination N1 and that actually that should be unattached. The M2 and N1 as at perpendicular. Very perpendicular. So for equal inclination, we get hydrogen fringes. Very good freeze out of this. Like this. And here we get concentric fringes. So we can measure this a little bit. That's by this equal thick fringes of equal thickness. So basically for that we illuminate the setup of fringes of equal thickness with white light. With white light fringes at the center of the field of view inside the transparent sheet in the beam path to the mirror M1. So the formula is mu is equal to n lambda 2t plus 1. T is the thickness between n and n. With this, we can also determine the wavelength of laser, observation of interference of white light, measurement of wavelength and coherence of LED sources, and also on and so forth. We can do this with, we can measure wavelength with Newton's determination of wavelength by Newton's thing also. So, let's make the formula. So basically, we know for right fringe, the n square is basically 2 into 2n plus 2n plus 1 lambda r. That is for right fringe. For the dark fringe, the diameter, dm is diameter of the image which will be 4 and lambda r. So if dm and dm plus p are respectively the diameters sorry the conflict for so thus if dm and dm plus p are respective to the diameters of the mth and n plus pth means right and dark, then the work length lambda is given by lambda is equal to dm plus 0 square minus t m square by 4 dr. Here t is the like number 1, 2, 3 like this. Counting the number p, we can determine the lambda, and that is how we can determine the lambda. There are lab practical depending on this equation. By the way, this picture is from the book written by P. Ghosh. And some of the content I'm discussing also got from that. It's a liquid. You can measure that using Newton's law. The Newton's ring can also be used to measure the refractive index of a liquid. At first, the diameters of the mth and m plus pth bright or dark rings are measured with air film. Then the diameters of these rings are measured again by forming a liquid film between the lens and the glass plate. The introduction of the liquid decreases the diameters of the ring. So, if you want to write this also. So, then we take the ratio. And always remember when we were doing that doesn't concern our 3D course, but when we are doing this lab practicals, uh, you need to measure, like one person need to measure all the nth rings, like fifth ring, seventh ring, or eighth ring, because when eyesight changes, this rings also appears different. So for you, it may be fifth ring, but for another one, when you need to focus during the experiment, you that another person can like can see that as the seventh bright ring. So person need to do the optical experiments at one go. Your film equation are dm plus pf diameter of m plus pf ring whole square minus diameter of m ring whole square, and the difference is 4p lambda r. We are taking like 5 inches for the simplicity. This process. This equation can press b m square that becomes 4p lambda r by n. So n becomes dn plus p whole square minus dm square at here, and this is dn plus p whole square minus dm square. So if you take the ratio, you get better. And that is not part of like this course, but for transmitted stream or transmitted light. The equation or like condition changes that optical path difference for this 2m lambda t for maxima. That was phenomena for reflected light and 2m plus 1 lambda e for so basically the dark region bright and the bright region dark. And the percentile fringe n is equal to 0 that is satisfied by this equation. And also there are different configurations. There is a make a distance between these two. Now, so from this to this, there is a thickness called x. So this is x. This is to be d. Okay. So d dash is basically d plus x. So the radius are, so the equation became 2nx plus n r square m plus p by r is equal to 2m plus 1 lambda by d. Sorry, this is for a method. Right tree. For n plus pth order right ring, the equation become 2nx. N r n plus p whole square by r, that is equal to 2n plus 2p plus 1 lambda by 2. So from taking this difference, you also get the lambda. So if basically we have moved the lens slowly in the up direction, so we will find the rings will converge at the center. We can determine the lambda by doing that also, that we move a known distance and then we will count the number of rings that have converged to the center. We can get the lambda. So when the lens is in, this is the one thing we can describe different uh, configuration. So if the lens is like this, the plate is also concave, then also we get different, like we get the bright ring and the dark rings, but their order get depend a bit different. So from that we can also, the lambda equation became, from this, dm plus b whole square minus dm square 4pr, we get like this. Here also for refractive index we'll get n. Here we get n dm plus b whole square by dm square by 4p, 1 by r1 minus 1 by r2. So what is r1, what is r2? So basically this is r1 and this is r2. Another configuration is like lens is contact with convex lens contact with concave surface. Contact with convex surface. So here the two lenses are like this. Instead of optical flat glass, we get this. So here the lambda is basically n dm plus p whole square minus dm square by 4p, 1 by r1 plus 1 by r2. So this is r1 and this is r2 basically. You can have look of the details of this calculation at the book by Professor B. Coach. So now we'll discuss some previous year quiz question. Into consecutive maxima in Fizeau fringe can be increased if, so fringes of equal thickness, this is sorry, it's not fringes of equal thickness, it's fringes of equal inclination, but that doesn't matter in our discussion. So we have seen the both fringes or equal fringes can be increased. The wavelength of the incident length is increased. That is true. We have seen that the distance between two consecutive maxima is proportional to lambda. then wedge angle of the film is reduced. So we got to know this is the wedge kind of experiment we are talking. So the equation was basically the distance between lambda f by 4 alpha. So lambda f is also lambda not mf into 4 alpha delta x. This is delta x. So wavelength. So delta x is proportional to lambda. So this is right. Delta x is proportional to 1 by nf. That is also right. So if nf got reduced, it will increase. And delta x is proportional to 1 by alpha. So wedge angle when it's reduced, it will be raised. So all of this. So this is the like my answer. The second question is a light wave is incident on the thin film of thickness 60 nanometer at an angle 30 degree from air. So n1 is 1. So basically sine theta I is sine 30 degree, just 0.5. Sine theta t is sine theta I into 1 by 2.6142. Here the refractive index of the angle, the film is 2.6142, which is given us 0.5 by 2.6142. So cos theta t became 1 minus sine square theta t, which will be 0.9815388 something. So here the question is optical path length of the reflected wave will be. So we know optical path length is 2nf d cos theta t, which is 2 into 2.6142 into 60 nanometer into 0.0981538. So the answer would be 307.9 nanometer. Next question is a light wave is incident on a thin film of thickness d nanometer at an angle theta I degree from air. If the refractive index of the film is nf and the refraction angle is theta t, the optical path length of the reflected wave will be, we know, is 2n fd cos theta t, and it can be written as 2d root over nf square minus sine square theta I. So you can write this thing and also the same first one, but here You can both mark, but here they preferred the second answer. Mhm. Then question number 4 is the maximum a thin film surrounded by air has an index of reflection of 1.3. So if a region of the film appears in this bright red, lambda 0 in normally incident light, then minimum thickness of the film would be. So for normal incidence, that would be 2nt is equal to, and bright fringe is m plus half lambda naught. So for minimum non-zero thickness, that is m is equal to 0, normally incident line, then minimum thickness, that is m is when m is equal to 0. So this became 2nt is equal to lambda naught by 2. So t is equal to lambda naught by 4m. We put all these values 4 into 1.3, we will get 102.30 nanometer. So this is the length. Because for 2nd cos theta t is the OPT. For normal incidence, this became 1. Theta t 0. So cos 0 is equal to 1. So I have written as t, but that can be written as t. And for non-millennium, here normally incident light, theta becomes theta t becomes 0. The next question, a thin film surrounded by air has an index of reflection of 1.58. If the minimum thickness of the film is 100 nanometers, then the wavelength of the normally incident light would be. So this is 1.58. A similar question as like the before. So we know T is lambda by 4n. So we are calculating lambda here. So that is 4nt. So 4 into 1.58 into 100 nanometer. And that is equal to 632 nanometer. So here, so this is the answer. Question 6 is very easy, straightforward question that Newton's ring experiments rely on. So we know that all in Newton's ring experiment, the amplitude got divided. So this is the answer, the interference by division of amplitude. Question 7 is if the path difference between two mirrors in Michelson interferometer is decreased, then the fringe pattern will be. So we know that this is the path, they are not an angle, so we are assuming that they are equal inclination fringes. We have seen in Newton's ring also that if the path difference between two mirrors is decreased, then they shrink towards the mirror, towards the center. So the reducing optical path difference reduces the allowed fringe order. So they shrink towards the center. A wedge-shaped film having wedge angle alpha is made up of a material whose refractive index is NF. If wavelength of normal incident light is double, then the separation between we know that X is, we have written that the first question that X is lambda 8 by 4 alpha. or you can say lambda naught n into 4 into alpha. If the wavelength of the normally incident light is doubled, so if lambda naught got to lambda naught, so delta L x will increase. The next question is a light wave wavelength lambda naught is incident normally on the wedge-shaped film of refractive index n. If the wedge angle, then the distance of the first maxima in the reflected light from the wedge angle will be. So first maxima occurs at, for the reflected light with 1 pi phase film, the first maxima occurred at m is equal to 0. So that is 2n f x alpha is equal to m plus half lambda naught. So that becomes 2n alpha x alpha, half of lambda naught. So lambda naught is given, alpha is given, n is given. So x alpha is basically 4nf lambda naught. And I put these values, that is 532. NF is 1.46, alpha is 0.2 billion. We put all this value, we get 455.148 nanometer. So that is the right answer. The 10th question is, our Michelson interferometer is illuminated with monochromatic light. One of its mirrors is then moved that and observed that 80 fringe pairs, but bright and dark, pass by in the process. The wavelength of the incident being variable. So mirror motion changes the optical path difference by 2 delta x, and the number of fringes is basically 2 delta x by lambda. So lambda is 2 delta x by n. So here 2 delta x is basically 4 into 10 to the power minus 6, n is 80. So this will give me as 100 nanometer. So that is 1 into 10 to the power minus 7. Basically. So this is actually 1 into 10 to the power minus 7 nanometer. So this is the answer. Now we want to discuss some other questions. Question 1. In Newton's ring experiment, diameter of emit dark ring is 8 millimeter and the diameter of m plus fifth dark ring is 12 millimeter. If the radius of curvature of the lower surface of the lens is 10 meter, find the wavelength of the light used. So we know lambda is basically d, what I have uh, proved here also. Here, so if the diameter of the nth ring bright ring, you get this dark ring. So if you do the calculation with any of the rings, you will get that equation here. Now we are using that equation only in this slide. So dm plus p square minus dm square by 4pr. So we know p is 5, then it is 4. R is 10 meter. And this dm plus p whole square is 12 millimeter, and this is 8 millimeter. So basically 12 into 10 to the power minus 3 whole square. This is 8 into 10 to the power minus 3 whole square. If we put these values, we get this value in meter. So when you put this value to the calculation, that will come to 400 nanometer. The next question, question 2. Newton's ring rings are formed in reflected light. (600 nanometer) with a combination of plain plate of glass and a plano convex lens of 1 meter radius of curvature. Introducing a liquid between the lens and the plate. It is found that the diameter of seventh dark ring decreases by 0.54 millimeter. Find the refractive index of the liquid. So the diameter dm square is basically 4m lambda r when the film is in the air. So for dark fringe, so dm is equal to become 4 into 7 to 600 to 10 to the power minus 9 because that is nanometer into 1 meter, that is 4.1 milliliter. And when there is a liquid of the refractive index n within the plate and the lens, the diameter becomes as 0.54 milliliter, so 3.56 milliliter. So here the dm square in liquid basically is 4m lambda r by n. So we know this is equal to, so m is basically dm square by air and d square by liquid. So they are basically 4.1 whole square. So dm air whole square, dm liquid whole square, and their ratio you need to take. So this become 1.326. This is the answer. Here m plus pth like fringe is not given. So you can a method of fringes has given. That is also the work. Question 3. Fringes are produced with monochromatic light of wavelength. Thin film of glass of refractive index 1.52 is placed normally in the path of path of one of the interfering waves. The central bright fringe is found removed to a position occupied by the fifth bright band from the center. Calculated. So this question belongs to the concept we have discussed last week. So, and maybe I have also discussed this question. So this is basically n minus 1 to t is equal to n minus. So t is basically n is 5, lambda is 689 10 to the power minus 9 divided by n is 1.52 minus 1. This is actually in meter, and that will give us 6.625 meter to the power minus 3 millimeter. The question 4 will be find the thickness and refractive index of an anti-reflection coating necessary for glass lens in air at wavelength 590 So basically the refractive and anti-refractive index coating is the concept is related to the thin film. So here we need that the reflected lights doesn't go into consecutive that R and R1 needs to form destructive interference. So there is no reflection. For that, so if that is M naught, that is air, that is in class, that is an air. The equation is M should be root over a multiple of N naught and Ng. So the R and R1 needs to form destructive interference with equal amplitude. Then can only it be zero. Form RC. So that is the condition. And also the thickness D can be measured as 2n C. The protein is C. Sorry, we can write as C. So the 2n in D is equal to lambda by 3. So D should be lambda by 4x. But we are only concerned about MC, which is 1.5 into 1. So that is 1.225, and the thickness should be lambda by 4 MC. So that should be 590 by 4 into 1.25 nanometer. We should be at 120.4 nanometer. The next question is in with light containing lambda 1 is equal to 589 nanometer and lambda 2 is equal to 589 to 9.6 nanometers. From the point of contact of planar convex lens with glass plate at which the rings. Okay, so we need to find the distance. Point of contact of planar convex lens with glass plate at which the rings disappear. Take the radius of curvature of curvature of the curved surface as 1 meter. So the fringe will disappear so the hint is fringe will disappear if emit order right ring of lambda 1 overlaps with emit order, because the difference in the wavelength is so small, so we are assuming that emit order bright ring will overlap with emit order dark ring of other wavelength. It can be that n plus 1 is the dark rings and also be like that. Lambda 2. Rn into n plus 1 lambda 1 by 2 into r. That should be n lambda 2 r. So then you can get, this is for the right fringe. This is the dark fringe. So then we can get by lambda 1 by 2 into lambda 2 minus lambda 1. It should be 589 2 into 1 6. That is 490. So 498 dark ring for lambda 2 and 490 bright ring for the lambda 1 is the distance of the receptor. So R 490. So we take this, that is 490 lambda into 589.6 into 10 to the power minus lambda 1. That is lambda and R to the what? So that is equal to 1.7 centimeter. At that distance, they will disappear. So there can be another question that question 6, that in an experiment set up producing Newton's ring, the radius of curvature of Leno convex lens is 1.45 meter. Find the diameter per ring and ring produced by light of wavelength. This is very straightforward question, 589 nanometer. So you know d square is equal to 4n lambda. You have seen this here. So d square is 4n lambda. R square is basically n lambda r. So this is 4 into 3 into 589 into 10 to the power minus 9. Into 1.45 meter, we get 3.2 millimeter. This is the answer. So that is for today. More concept will be discussed in the next video. Thank you.